everyone. Welcome. We'll go ahead and get started. Most of you know me. My name is Tony Graham with the Wheatland Lab, and welcome to this afternoon's Wheatland seminar. This afternoon we have Justin Schlawin with us from the Maine Natural Areas Program. He's an ecologist with Maine Natural Areas Program. He's been there since 2012, specializing in GIS interpretation and analysis. His work has included rapid detection of vernal pools through remote sensing, gap analysis for habitat underrepresented in Maine's conserved lands, and collaboration with regional conservation partners to incorporate climate resiliency science into their planning. His other duties include botanical field inventories of public lands, floodplain wetlands, and monitoring state ecological reserves. Let's welcome Justin.
Thanks, everybody. I don't know if the microphone can hear me here, but I thought to break the ice, we'd go through and identify some of the things on these images up here. Maybe you can have some students help me with this. Does anyone recognize this critter here?
Come on, I'm not even a wildlife guy. I know what that is.
You're not a student, I know that. Yeah, and then do people recognize the egg masses there? Anybody recognize what species that might be? These are wood frog egg masses, and I'll point this little bait net shows up in a couple of these photos. This is a great tool for scooping fairy shrimp if you need to photograph them for the state determine whether or not it's a vernal pool, it's a statewide significance. So here's a fairy shrimp. This is a Philippe Monadier that's in this vernal pool. If you get more than one of those in the pool, it could be a significant vernal pool depending on what else you find. So I'm going to talk about two different projects where we've used some remote sensing techniques to find vernal pools in Maine. So I work for the Maine Natural Areas Program. We work together with IFNW to be a comprehensive resource on information on the state's important natural features. Our focus is primarily on botanical features. So we track the locations of rare plant populations, rare and exemplary natural communities, and we also work with invasive plants. So vernal pools is a little bit outside the core of what we do, but we have some GIS expertise in our office, and vernal pools are a habitat that is defined by some hydrological, geological factors. So there is some crossover. Oh, and I should mention, we're in the state's Department of Agriculture, Conservation, and Forestry. So in this talk, we're gonna go through quickly define what a vernal pool is. Maybe I can get your help with that. I'm going to talk about a project where we used some remote sensing techniques to predict vernal pools in wildlife management areas that we completed in 2016. And then lastly, and probably for the majority of this talk, I'll talk about our most recent effort in southern Maine, the Mount Agamenticus to the Seas focus area, that's a conservation organization where we really improved our techniques to identify locations of vernal pools in the landscape. So let's see, another question for the audience: what is a vernal pool? Any takers? Just throw something out. Now everybody's allowed to answer.
What if it's not there all the time?
Well, we'll just maybe I'll make someone. You got something there, Joe?
Well, let me try this. It's a pool that gets flooded in the springtime, dries out over the course of the year, doesn't have a natural outlet, isn't free flowing water. That's about as much as I know, or I think I know.
I'll add it's fishless.
Important for amphibians to breathe in.
Right. So now I can just leave. You guys know everything. I don't need to talk about this anymore. Yeah. So you've captured the elements of what is a vernal pool. We're not going to read the long definition here, but the sort of the key elements are that it's it's defined both by biological characteristics, so indicators, species, and hydrological characteristics. These are ephemeral places that can't support fish or other predators that prevent these indicator species from occurring. And they're also small. They're typically less than 2 acres in size. Philip, do you want to contribute anything else to that?
No, that's good enough.
Because it's a fairly broad and wide-ranging definition, it makes some challenges to identifying these on the landscape. Traditionally, the methods have pretty much been analog detection of vernal pools, so studying aerial imagery, either digital imagery or through stereoscope to find vernal pools. And that method is very accurate, but also quite time-consuming. So the goal in both of these projects was to develop some automated methods that could hopefully at least match the accuracy, possibly improve on the accuracy, finding vernal pools in the landscape that would be significantly more efficient than just studying the aerial imagery. So one of the challenges, as I mentioned, to finding vernal pools is that they can occur in a wide variety of locations in the landscape. This is just a simple graphic, kind of indicates that vernal pools can be parts of shrub swamps, they can be within river floodplains, they can be isolated on the landscape, or connected to intermittent headwater streams. So here are some images of just some of the different settings that these vernal pools can occur in. So this is a floodplain pool, upland basin pool, some shrub swamp pools, forested swamps. So when we think of vernal pools, typically we are thinking about these isolated upland depression pools, shown in this image here, and what these might look like on the landscape. If you can see this yellow arrow, it might look like something like that in the aerial image. So that has a specific signature. But places like this kind of open marshy wetland could also be a vernal pool, and that might look different in the aerial imagery and in the remote sensing data. Or these shrub swamps might look like this area up here. So, so that's part of the challenge in finding these places is they can look quite different and they can have quite different hydrology. Some of the vernal pools can be part of much larger wetlands, perhaps a small part. So identifying those locations can be very challenging. So in our first crack at using these remote sensing tools to find vernal pools, we were focusing primarily on wildlife management areas in southern Maine. And the basic method that we used in both projects that we worked on was to identify depressions on the landscape using hydrology tools, and then determine which of those depressions were too dry to be vernal pools, and which of these depressions were too wet to be vernal pools. So it's the Goldilocks scenario. You know, the Goldilocks is the vernal pool, and the porridge too cold is maybe the too dry, and the porridge too hot is the place that's too wet. So with this wildlife management area study, our study area was almost 1,100 kilometers squared and included 13 wildlife management areas and a surrounding envelope around these areas. So this is the study area. So one of the key elements to being able to do this work is working with a LiDAR derived digital elevation model. The higher resolution a digital elevation model you can generate or produce, the more accurate your mapped depressions are going to be. And I'm going to explain what that is in a second. And so it's higher nominal point spacing in the LiDAR allows better digital elevation models to be produced. So from the LiDAR derived digital elevation model, we use some basic hydrology tools available in ArcGIS to find depressions on the landscape. And depressions are places that if you were to pour water all over the surface, there would be places where the water would pool and not run off in the elevation model. So this is an area of the Alonzo Garcelon Wildlife Management Area. This is a hillshade layer derived from the digital elevation model. This is a high resolution aerial image of the same area from the Maine Geolibrary's collection. And I'm displaying it in color infrared type of display here. And you can see there's several areas that are darker here. These are vernal pools here. So this was kind of the area that we used to sort of examine and work on our methods. So using these basic hydrology tools, we're able to calculate not only the locations of these depressions, but the depths of the depressions. So as you can see, it captures a wide variety of locations on the landscape at a variety of scales. So to filter out the noise, we removed depressions that were too small and used some morphology operating tools to sort of simplify the depression locations. So comparing that to the aerial image, we have the map depressions include places that are vernal pools. They also include areas of dry upland forest that are might be puddles in early spring, but probably not vernal pools. Can include some sort of more complex swamp features that may or may not be vernal pools. In this case, this is a hemlock-dominated wetland. It can also include roadside ditches, empty swimming pools, any kind of other depression on the landscape. And that's going to be a potential source of error. In this project, in our state wildlife management areas, we did not correct the, we did not hydrologically correct the digital elevation model. And the reason we did not do this was that we were focused mostly on natural areas, but this led to a major source of error in our data in the surrounding envelope around wildlife management areas. Because, and we'll look at this in a little more detail later, but the digital elevation model produced from LiDAR, the roads and other human-built features become impediments to the flow of when you're modeling hydrology, and they become artificial ponded features. So in order to map vernal pools in suburban, urban settings, that needs to be accounted for. So to find the places that were too wet, we used thematic data such as the NHD layers, water bodies, flow lines. We also used flow accumulation data, which is the amount of area for any given point on the landscape to which water would flow into that, or the number of pixels upstream of that location. We'll look at that again later on. To determine places that were too dry, we did an image analysis that relied on the low reflectance of water in the near infrared spectrum. So soil and vegetation has fairly high reflectance in the near infrared spectrum, but water has nearly no reflectance. So this is a leaf-off near infrared image of that same area, showing just that near infrared band, where you can see darker areas have very low reflectance in the near infrared spectrum, and higher values have more reflectance. So we're able to classify these depressions by these near infrared values to predict vernal pools. We also classified these depressions by their geophysical setting, simplified into 4 categories. So unstratified glacial drift, coarse deposits, which was mostly sand, marine clay, and peat and muck. And we had to tune the individual thresholds of each of these variables in this process differently depending on what setting these depressions were in, because the hydrology of the potential vernal pools would be very different in these different settings. Okay, so we used a process in this project that was it was basically a decision tree process. It was not a advanced machine learning process. We did very little training data for the areas we were looking, and so we essentially set thresholds for each of the different variables manually, and use that to predict where these potential vernal pools are. And we wound up grouping depressions into these three categories. Well, I should say there's four categories. One category is to be excluded from consideration. And then the other three categories are based on the hydrology of the site, whether they're likely a ephemeral pool and are not supporting indicator species, whether they're a potential vernal pool where there's strong evidence from the imagery, or whether they're likely a perennial wetland or pond where the overland flow was too high for them to be likely a vernal pool. And then we did some field validation of these sites based on stratified by the hydrological classification and by geophysical setting, those four types that I talked about. So this is what that map looked like. And these are the different kinds of things we were finding there: from spotted salamander, egg masses, a sort of amorphous shaped vernal pool, and a deep open basin pool. And our results in this project varied considerably by the setting that we were working in. So we had pretty good results in till settings. These were mostly our upland vernal pools, with comparatively poorer results in our other settings. Overall, we had about a 72% accuracy rate. And this is sort of comparable to some other studies that have used analog imagery. But all of our field verified vernal pools were within our wildlife management area, so they were in natural settings. And we weren't evaluating the accuracy of potential vernal pools outside of the wildlife management areas. So in developed areas, we expected it would be quite worse. Our omission was fairly high in this project. And again, this is related to where the existing known vernal pools were located. Most of the assessed vernal pools in this study area were assessed for environmental review purposes, and they were on power line corridors near development. And because we did not we did not correct the DEMs to match the hydrology, a lot of the error was associated with that. So with our next project, we knew we could do much better, but we found that this method was pretty effective for undeveloped settings, but that we could improve it by improving the hydrological correctness of the digital elevation model, as well as coming up with some new methods to find vernal pools in large wetland settings. So an opportunity to jump back into this work came along last year. The Mount Agamenticus to the Sea Conservation Initiative contacted us about mapping potential vernal pools in the 6-town region covered in their focus area. So that includes all of Wells, South Berwick, Ogunquit, York, Elliott, and Kittery. And this was actually initiated, if any of you are familiar with the Special Areas Management Plan associated with vernal pools. Kittery was engaging in or is considering engaging in that program. It's a mitigation program for vernal pools. And so they sort of initiated the project, and then the rest of the Mount Agamenticus to the Sea Conservation Initiative jumped on board and funded us to map potential vernal pools on the landscape here. One of the really nice things about doing any sort of mapping or modeling work in this region is that there's a ton of field data for this region. It's a very well studied region. And we had a large number of mapped vernal pools in the IFNW's significant vernal pool database that were mapped in this region. So we felt we could really improve. This would be a great place to work on improving our methods. And so our approach was very different in this project. How many of you here know about random forest? And have you folks used it? I feel like when I come here, I'm in the land of the random forest. That makes sense. So we had a lot of field data that we could use to train a model in this area. So there were 250 field verified vernal pool points in IFNW's data just for these 6 towns. And we were able to then associate those field verified vernal pool points with the LiDAR modeled depressions and then using a number of other remote sensing data sources, thin out the error and predict a model, a potential vernal pool map for this town. So we'll go through sort of step by step what we did here. So the first step, similar to the previous project, we calculated these depressions across the landscape, but we had to correct the hydrology in order to have better predictions in suburban areas. So as we saw in the previous project, we calculated the sinks using these hydrology tools, but here we, I should point out, you see this sink in the top left-hand corner. So some of these areas seem like they're valid depressions on this landscape, but other areas are greatly expanded by their adjacency to roads and development. So this area on the top left corner here, that is, if you look in the aerial photo, it's really not a big, large basin depression here. Also looks like there's been some, I don't know, some ditching in that site as well. And part of the reason that looks so big when it's modeled as a depression is that the LiDAR doesn't see the culvert that's right there, and then also further downstream from this site. So using a script that Dan Coker at the Nature Conservancy developed that he calls the Ditch Witch, we were able to drain these artificial depressions. And what this script does is basically look for the lowest point in each depression and then find the next lowest point on the landscape and draw a straight line to those 2 different places. And anywhere where these lines are intersecting with roads or other built features, they pretty accurately describe where the locations of culverts are. So after that script is run, we can then look at this new depressions layer. You see that a lot of them have shrunk considerably. Okay, so then the next step is to link our field data to those depressions. So in this area, there were a number of mapped vernal pools in IFNW's vernal pool database. And they really had to be linked manually to the mapped depressions, just in part because the scale and the accuracy of the mapping is quite variable. So this mapped vernal pool right here seems fairly true to the mapped depression, but the geometry of this one clearly there was a different sort of resolution of information provided to IFNW. And so in the case of this vernal pool here, based on the size, the anticipated size, all these depressions in this area were linked to that vernal pool. And so but as you notice, there's actually quite a few of these different depressions in that area. So the there was a one-to-many relationship between the vernal pool database and our map depressions. And that'll, when I'm reporting on some of the validation results later, that actually comes in, is important. I should also point out that there were 88 significant vernal pools mapped in the study area, and 86 of those could be linked to these depressions, and only 2 could not be linked to the map depressions. But upon closer inspection, it looked like both of the mapping for those 2 vernal pools they were placed in the wrong place in the database. So it captures pretty much the full extent of what could be a vernal pool on the landscape. And we'd be all set to go home at that point, except that we mapped over 200,000 depressions for these 6 towns, and probably only 1 to 2% of those are actually vernal pools. So that's why we need to do the rest of the modeling. Next, our variables included aerial imagery variables, hydrology variables that were calculated from the digital elevation model. We gathered forest canopy information from the LiDAR point cloud, and superficial geology information, as well as other wetland data such as National Wetlands Inventory data, NHD data. And we had over 100 different variables that went into this model, and we trimmed that to 36 different variables. And we'll look at the variable importance in a moment here. But the reason we probably could have used even less, but I wanted to be able to demonstrate that we tried using a number of different things that were reported in the literature for other folks that had done some remote sensing for vernal pools. So this is this is a near-infrared image that was used in the model where areas of low reflectance had higher probabilities of being a vernal pool. We calculated the normalized difference vegetation index, which in the leaf-off imagery is a good predictor of conifer forest, and can be used to add some uncertainty to the model for conifer forest areas. We also used imagery from NAPE, which is now being collected with an infrared band. This is the normalized difference water index, which is another calculation you can do from an image that leverages the low reflectance and the near infrared band to predict water. We also used the intensity values from LiDAR, which is also flown in the near infrared spectrum. So low reflectances correlate with water pretty well. We used synthetic aperture data from a Japanese satellite, the Pulsar satellite that flew from 2006 to 2012 when it was struck by some space debris. And the incidence angle of this satellite has been shown in some studies to be a good predictor of water in certain times of the year. As I mentioned, we also used some of the NHD data. In this case, it was a distance to flow line, distance to water body value. This is that flow accumulation data that I was talking about earlier. This is not only a really good way to describe whether or not a depression might be a perennial wetland or not, but is a really good way to find the locations of streams. Superficial geology data. This is a LiDAR-derived vegetation density map, and what you're seeing here is actually this is the line between collections. The southern Maine LiDAR is not at the same quality metrics that it's been flown for the rest of the state, so there's a fair amount of error here, but we threw it in the model anyway, just to see what would happen. And then we used rainforest to create our potential vernal pool map. So this is this is the variable importance chart here. So we'll take a moment to look at this more closely. see what were important variables in predicting vernal pools and which were less important. So our high resolution imagery, near infrared imagery, was the most important variable in predicting vernal pools. And then other things that were very important were some of the wetland data that was used to help basically predict whether or not these places were ponds or lakes. What was interesting is, some of these things that were a little less important were a little bit surprising, such as some of the NWI wetland data was not very useful in predicting whether or not it was a vernal pool or not. We can, if in the question and answer session, if you guys have questions about any of these things, I'm happy to go into a little more detail. I'll also point out probably the most time-consuming variable to generate was this thing called the stochastic depression value, and there's some published literature that was able to they used this metric to identify artifact depressions from true depressions when predicting potential vernal pools. And the way it works is you create random digital elevation models based on the error of the LiDAR, and then you calculate a new depression value for the randomized digital elevation model. And then where there's a lot of agreement in the depression value, in where the depressions are, it's a better predictor, I guess, of being a true depression. And so this is something that I had to kind of, on a Friday evening, run the script all weekend, and it would maybe go through 5 or 6 iterations, and then turn it off on Monday, and then do that the next Friday. And ultimately, it probably wasn't worth doing any of that because it has pretty low value in the model. So next time we can forget about doing that. It doesn't really help us. So a quarter of our field data was reserved for map validation. And our accuracy, I kind of wavered between choosing a 4-fold plot here or a confusion matrix to, which would be more confusing for you folks. The key take homes here is there's a commission error rate where we had false predictions. 17% of our predictions were false when we used our test data, and we missed 18.5% of the vernal pool depressions that we'd identified. So, but I want to point out something. There's definitely bias in our training and our test data. We know that vernal pools, there's probably about 2,000 to 4,000 vernal pools in these 6 towns, and we'd mapped over 200,000 depressions. So that's about 1 to 2% of these map depressions could be vernal pools. But in our training and test data, vernal pools accounted for 1/4 of the depressions. So we knew we were over predicting vernal pools in this model. So our error of commission is likely higher than that if we were to do a field test of this model. However, our error of omission is actually likely less than this. I inspected all these places where we had failed to detect vernal pools, and most of these areas were portions of map vernal pools that actually looked like they were inclusions but weren't actually vernal pools. But without some sort of other way of verifying our accuracy, this is kind of what we're reporting here to our partners. So there's a great quote from Woody Guthrie: "Any fool can make something complicated. It takes a genius to make it simple." And so our partners here, the Mount Egomenicus to the Sea Conservation Initiative, really just need a simple map at the end that shows where these potential vernal pools are so that they can make decisions about conservation actions. And so I took our predicted vernal pool map, and I decided I needed to really just simplify our potential vernal pools into high, medium, and low probability classes. And so using the importance function in random forest, we're examining here, what we're looking at this chart is the relative importance values of different these different depressions and how they're classified. And it's pretty clear that importance value, confidence values of over 0.75 had a really high probability of being a vernal pool. Confidence values between 0.5 and 0.75 had a sort of intermediate, medium confidence value, and then values below 0.5 had a pretty low confidence value. So binned all our potential vernal pools into those three categories. And this is what that map looks like in the landscape we were just looking at. And I also point out we simplified the geometry further based on those three categories, so that it was a little easier to interpret. So I'm going to just take a few minutes now. We're going to roam around southern Maine and look at how this model performed in some different areas, some natural and suburban areas, as well as some areas with large wetlands. So one of the interesting things about York, Maine is the density of vernal pools here is extremely high, and sort of reflected in this image here. This is an area of York where in yellow we're looking at these high confidence vernal pools, and in purple these are sort of our medium confidence potential vernal pools. I feel like, you know, in these natural settings with isolated upland pools, we really nailed it. This is another area, natural settings with a little bit less density of vernal pools, where maybe there's a little less value in those medium confidence potential vernal pools, but those high confidence potential vernal pools seem quite accurate. Here we are in a more suburban setting, where the source of error and human impacts to the landscape can add some complicating factors, but we seem to have captured these areas that were near development fairly well. However, we might have some error here. This looks like some sort of ditched wetland here that may or may not be a vernal pool. Probably wouldn't be a vernal pool in terms of being a significant vernal pool because of human impacts, but could be. Can't know until you do field survey. Here's another area of the map in a suburban setting where this really interesting shape of a potential vernal pool here. And then here we're starting to look at some larger wetland complexes, and these are places that we're mapping potential vernal pools, no matter what method you use, is really challenging. What portion of this large wetland here could be a vernal pool, if any portion is, and without additional field verifications, it's going to be difficult to know how well this model performed in these areas. But it seems like a fairly reasonable guess based on just studying the areometry that these places could be supporting some indicator breeding areas. Here's another area of some larger wetlands with specific areas identified that could be the vernal pool component of these larger wetlands. Here's another larger wetland complex. And here's sort of just expanding in scale here and complicating factors. This is clearly an area where our medium confidence vernal pool areas are probably pretty inaccurate, but some of these high confidence vernal pool areas could be pretty good. So some of the takeaways here is that we determined that there's some areas of high density vernal pools in all 6 towns in this study area. Overall, there's 5.6 vernal pools per kilometer squared. The lowest density in Wells, and then the highest density in York, and that's been fairly well established. Aram Calhoun's done quite a bit of work down here, and has she established that in an area sort of between York and North Berwick, there's somewhere between 13 and 50 vernal pools per kilometer squared. And the darkest blue, and I don't have the scale shown here, but the darkest blue in our in this heat map here indicates areas of between 40 and 50 vernal pools per kilometer squared. So we were pretty consistent with what she's reporting there. Fred DeBello did some work in a number of Maine towns from aerial imagery and reported roughly 2.7 pools per kilometer squared. Work in other states is at a comparable scale, with one outlier, and this is that study that used the stochastic depression analysis, where they found really high numbers of vernal pools per kilometer squared. So with that, I'll take questions.
So you commented that the LiDAR for southern Maine was not as well quality controlled as some of the later stuff that's come out. Have you played in areas where you have better LiDAR data and seen if that improves the process?
It does. Our first project, the wildlife management area project, we had a lot of areas with higher quality LiDAR, and portions of this study area had some higher quality LiDAR, but it's usable, the stuff in southern Maine. It's just patching it together. And some of it was like the LAS data is in feet and not meters, and so it's just kind of, it's really messy. And then for as far as the digital elevation model, it's usable. We did some evaluation comparing DM resolutions of 1 and 2 meters with our wildlife management area work, and we definitely got better results with a higher resolution DEM. So I think, I'm not quite sure if it would matter at this point in the Madagascar Sea area, but a lot of just the workability of the data was sort of actually the main issue in making putting a square peg in a round hole.
Was it all was the time of capture, the seasonality of the capture for the LiDAR important?
It is actually it is a consideration. To whether it added to error or not is kind of unknown. Those LiDAR intensity values are going to be less useful if it was flown in the fall. But they weren't really an important part of the model. Random forest kind of sorted that out by itself. The one thing that does happen is that because you get such low reflectance in the near infrared spectrum, that basically there's voids in the point data from LiDAR where it hits water, and so sometimes the accuracy of mapping the vernal pool boundary is missing the wettest part, because the digital elevation model for that area has been interpolated based on other sort of other higher features, or it adds slope to that area. So that's certainly a source of error, and that actually happens when the LiDAR's been flown earlier in the season as opposed to later. So there's a couple of different complicating factors to be considered.
Because there's more water earlier.
So when the vernal pool is full of water, there's the sort of the wettest part of the vernal pool might not be reflecting or returning those LiDAR points.
Yeah.
So the digital elevation model that you generate from that will not be accurate to what the vernal pool is. So it's actually, if the LiDAR itself is flown in the spring, then the intensity values become more useful. And I didn't mention, I did actually try to correct for that. So I found places where there were really low LiDAR intensity values that were sort of nested within depressions, and just included that as part of the depression to try to help iron out some of that, the wonkiness in how these want to be mapped because of that. Good questions.
Just go back to the variable slide. The variable performance evaluation. Just being more of a naturalist and a field biologist, I'm just kind of reflecting on some of these and the meaning of them and how interesting they may or may not be. Just thought you might be able to think out loud too. So it's interesting because your wildlife management area project that we worked on a little bit together, that was the precursor to this. The superficial geology, it performed it just way better than till, and yet it looks like your till here is the least useful. Compared to the other superficial geology settings.
I think, one thing, the variability was quite a bit less in the superficial geology at this site versus the wildlife management area work we did, where we were in pretty dramatically different parts of the state, and so I think that probably had something to do with it, but with using random forest, it's hard to know exactly what the algorithm's thinking, but were we to remove certain variables, some of the importance of some of those things might have been greater, but so what we found in the wildlife management area study is that the flow accumulation, I don't know where it is on here, there it is, that was pretty variable for different vernal pools, depending on setting, but that may have been sorted out differently. But I think mostly it has to do with there's just not that much variability across the whole 6-town region. There are some areas of marine clay, but they don't seem to be, that's not the same as like wildlife management areas around Merrimack Bay. And same with the coarse deposits. There's just a lot of the coarse deposits here were really developed. And so it just may not have been characterizing those too much. And it may also have to do with the location of our training data. It could be another, because it's not just our training data wasn't just random sampling of all vernal pools. We randomly sampled the training data and separated from the test data, but it could be that there was some added bias in our training data. I didn't mention that we and I should have, that for our training data, we spent quite a bit of time inspecting aerial imagery and identifying negative data points, because as many of us have experienced, it's very sometimes a lot easier to come by confirmations than confirmed lack of presence. So the IFNW data set had just way fewer negative data points, and so the way we accounted for that was inspecting aerial imagery and randomizing depressions across the landscape, and just if they were definitely not a vernal pool, they were classified as such.
The good stuff up at the top there makes me happy because in class, students, they just want to know about LiDAR and it's the greatest thing ever, and then like imagery is stupid. But look, so, but the imagery is that GeoLibrary stuff, that 2012, that's like wicked high resolution. Right?
Yeah. So this was, I think it's a 6-inch, but actually resampled it all to 1 meter because otherwise it was really hard to process it. But for this, you know, I just resampled it looking at the minimum value, so I didn't actually lose anything. But actually, one thing I was really impressed by was the performance of some of the NWI, or so not NWI, the NAPE data. And I did some testing, and I unfortunately didn't have enough time to really fully investigate this. But so long as we had good training data, I did some testing where we took out the GeoLibrary imagery, because that's basically the only thing on here that we don't have for the entire state. I took that out, and I just to see how the model would perform without it once we had our good training data, and or how well a model you could build without that. And turns out you can build a very good model without the GeoLibrary imagery, because the NAPE imagery still had a good enough signature near thread spectrum.
Well, that was my next question, because the GeoLibrary stuff is also, that's leaf off, right? Whereas the NAPE is leaf
so
on,
that
so
was,
you wouldn't expect the NAPE to be able to see through the camera.
Yeah.
So I was going to ask if you noticed any difference in how well you can detect these in hardwood versus, or deciduous versus evergreen. Or if they just don't occur. I don't know much about vernal. They would occur.
They occur in both settings. This area is in southern Maine is pretty. There's a lot of hardwood, but there's also quite a bit of mixed forest, and it's mostly pine and hemlock and not spruce and fir. So, but it seemed to perform pretty well in those settings. Hard to know without doing some testing how it would perform under spruce fir forest. But in most of the other studies that have been done to predict vernal pools using these remote sensing tools, they've reported much lower accuracy in conifer forest. But they were also not using such a laundry list of variables, and so I don't think it mattered that much for this region, but again, to be determined. The one thing is that even in conifer forests, most vernal pools, if you have fairly high resolution imagery, there's at least some area where the imagery will have sort of picked up some area of water. Even if you can't really see it so well yourself, the reflectance is even lower typically than shadows cast by conifers. But yeah, spruce and fir might be not as good. I probably wouldn't want to run the same model on a spruce fir area without doing some testing and having some training data from those areas.
How do you determine that break in your high and medium value, the yellow and purple?
It was based on the what's it called? The probability function of random forest, where random forest uses, perhaps somebody else here will be able to explain this more articulately than me, but the way random forest works is it builds many different decision trees, and they're random decision trees with selections of the variables that you choose, and basically the probability function is the percentage of the trees that were sort of agreeing here. So 75% of the trees, decision trees, agreed that these ones here were vernal pools, whereas 50 to 75% of the decision trees were agreeing that this test data was vernal pools. So we knew that that there was almost 0 false positives in this highest level of this highest category. And then as we went lower, so just set thresholds at 0.75, 0.5, and then below.
Okay, so the medium values are down to 75.
Yeah, and I wasn't displaying the low values on the map there. There's a lot more error there, so in the model, these were still areas that were more probably vernal pools than not according to the model, but they were because of that bias in the training test data. There was actually just a lot more error in these lower categories.
Going back to your omission commission matrix there, your 2x2.
Yep.
Did you try just saying, well, what if I took the pools that were the largest and only put those in this figure? Because I mean, obviously, what you expect is that the small ones are the problem ones for both omission and commission. Did you look at that at all to see if something like that was going on, or if you could sort of?
What's tricky is that you notice I mentioned we had 250 vernal pools in the vernal pool database, but our test data so you look at our test data here, and we have significantly more data points in our test data, and that's because of that one-to-many relationship between our map depressions and vernal pools.
So you're getting multiple depressions per pool, or?
Yes.
Okay.
Yeah. So to know what yes, we are probably missing the smaller. The ones that we were missing were smaller ones, but as I mentioned, many of those were actually incorrectly mapped.
Mm-hmm.
I'll just point. I didn't show this figure, but I did chart out histogram of the side at the very end. Bear with me here. This is the count of vernal pools by area. So here we have, this is our high confidence vernal pools. And so we're detecting vernal pools, and I didn't mention, but our minimum mapping unit was 25 meters squared. And so we had a lot less confidence in these small ones. But there were some small ones that were for which we did have high confidence. But there's sort of this sort of sweet spot here where most of them were about 750 meters squared.
Any other questions for Justin? Okay, just a quick announcement. 2 weeks from today, the final Wheatland seminar for the semester is going to be Dr. Phil Townsend coming in from the University of Wisconsin-Madison. And he's going to speak about folio traits and ecosystem function at broad spatial scales using imagery spectroscopy. So please join us for that. And that announcement should go out tomorrow or Friday. And then we'll reconvene at the Tim's Chat Room in Orono this afternoon. So thanks, everyone. Thanks, Justin.
Thanks, guys.